So the first couple questions give us a table and they ask us to generate a couple things with them. One of them is to extend the table to the fourth term. One is it asks what the generator is, and that'll be different depending on if it's arithmetic or geometric, what kind of sequence it is, how can you tell, and finally write the explicit equation for the sequence. So the first one up there is it is geometric, and I know this because if I start with, for example, 8 and I multiply that by 3, I get 24. And if I multiply 24, not by 2, but by 3 again, I get 72. And extending that to the fourth term, I get 3 times 72 is 216. So if I complete the table for the fourth term, that fourth term would be 216. I can write in this box as well. What is the generator? I multiply by 3 each time. What kind of sequence is this? This is geometric. How do I know? Because it has a common ratio, right? I keep multiplying by, not ration or ratio. I keep multiplying by 3, right? So it's multiplied by the same number repeatedly. And then finally write the explicit equation. It doesn't say standard form for a sequence, it says explicit equation. So remember, for geometric, we've got y equals a times b to the n power. This is the 0th term, and this right here is your multiplier. Now, the one thing that we don't know is we don't know the 0th term. So to get that, I'm going to have to take the 8 and divide it by 3. So my 0th term is going to be 8/3. So I'm going to start with 8/3. And every single time after that, I'm going to multiply by 3. And in fact, I'm going to multiply by 3 and repeatedly. So it's going to be times 3 to the, if I'm doing this as an equation, I should use an x there. And I should use an x here. So each time I'm going to continue to multiply by x. So that is the example that's geometric. And you'll definitely see a question much like this on the test on Monday. Here's another possibility. I'm going to leave this one for you to do on your own. I will point out, however, that this time it is not, I repeat, not geometric, because we are not multiplying by the same value each time. We're adding a constant each time. The next series of questions I have for you involve some expressions with exponents, negative exponents, some powers raised to powers, and I ask you to simplify them. I'll just point out a couple things, and I guess we'll do the first one. So if I look at this, one of the things I notice is that these, right, those factors can be relocated into the numerator, and I can show that a couple different ways. Or I can just remember, kind of how to deal with this from a rule-based approach. One of the things I consider is, for example, this 1 over b to the negative second power. So you can see I've got a b to the negative second power. What is that equal to? Well, if I multiply this by a giant 1 in the form of b squared over b squared, notice this numerator is b squared now. 1 times b squared is b squared. The denominator is b to the negative 2 plus 2, which of course is the same as b to the 0 power, which of course is equal to 1. So this becomes, if I look at this, it becomes b squared over 1. So kind of the shortcut thing we think about is if we're looking at factors, it's all multiplication, and I have a negative exponent either in the numerator or the denominator, I can relocate that to the other place. If it's in the denominator, it can move to the numerator, for example. Let me erase this. So what I can do is I can transform this as follows, right? I can write the ab cubed, and then I'm going to bring up a b squared. This b squared, right, is the one that was in the denominator and it was negative. Now it's not in the denominator, it's up in the numerator. And then I can multiply by a b squared, and then this I can multiply by a to the 4th power. Notice it was a negative exponent and it was in the denominator, and I've moved it up top. What's nice about this is now I can see that I can just go ahead and combine all of these parts. If you look, I've got right here, there's 3 factors of b, and then 2 more factors of b, that's 5, and then 2 more. So that is a total of 7 factors of b. So I've got b to the 7th in my answer. And then I've got a factor of a, and then 1 more factor of a, so that's a squared. And then I've got 4 factors of a, so that's a to the 6th power. So you can either write your answer as a to the 6th times b to the 7th, or b to the 7th, a to the 6th. So without doing the other questions completely, just a couple pointers. For example, this part right here, I could choose to rewrite that as 1 over 3x y squared, and then raise that to the 3rd power. So you can see now I don't have this raised to the negative 3rd issue. So that's part of that problem. And then I have to multiply it by this thing as well. But this part that I'm doing, I could now raise that parentheses to the 3rd power. So that becomes 3 to the 3rd, right? This 3 to the 3rd, which is 27, and then times x to the 3rd, and then times y to the 2nd to the 3rd, right? So if I have 3 factors of y squared, that's y to the 6th power. And this is all still down in the denominator, right? But I can multiply and still bring this piece into it. So let's just not say any more about that. If I look at D, the first part, I could look at just this section of it right here. That is a to the 3rd, and then b to the negative 6th power. And then I could rewrite that as a to the 3rd over b to the positive 6th power. So you see how that changed. And then I've got times 1 over 2a, and then times, I'm going to write this as a cubed over 1. So if you look at my numerator, right, I've got 3 factors of a and 3 more factors of a, so that's a to the 6th power. And then down in my denominator, I have b to the 6th times 2, and then 1 factor of a. If you don't see an exponent, right, it's implied that it's a 1, so that's a to the 1st power. So if I have 6 factors of a in my numerator and 1 factor of a in my denominator, that they'll cancel out, one of them will, and I'll be left with a to the 5th power up in my numerator. And then I'm going to go ahead and write the 2 in front, 2 times b to the 6th power. So that's actually the complete answer for that. So I did D and A completely. I did part of B, but you guys should be able to figure out how to complete C. So 2 problems here. Find the equation of a line through a couple different points. Pretty standard problems. We've been doing these for a while. I'm going to go ahead and do the second one with you and go through all of the steps. So our general strategy is to use the 2 points to get the slope. And then after we know the slope, we're going to use the slope and one of the points to get the y-intercept. And then finally, once we have the slope and the y-intercept, we can just write the equation. So let's start by finding the slope. Remember, the slope is how much y changes divided by how much the x values change. And to show change, we're using subtraction, right? The difference between the 2 different y values over the difference between the 2 x values. And I'm going to go ahead and go from this point to the second point. So for each of the coordinates, for y's, I'm going to write 2 and then minus 4. And if you see 2 minus 4, and then for the x's, I'm going to go same direction. I'm going to go the 9 minus the 6. So if I look at that, 2 minus 4 is negative 2, and 9 minus 6 is 3. So I know that my slope is equal to 2/3, and we're now going to use that and one of the points to find the y-intercept. So to find the y-intercept, I'm going to use this equation, right? The slope-intercept form of an equation. Y equals the slope times a particular x value plus this y-intercept that we're trying to find. That's the value, the variable we're looking for. And if I wanted to actually solve this equation ahead of time, I've never thought about doing this, but I can go ahead and solve for b right now by subtracting mx from both sides. So y is equal to, I'm sorry, y minus mx, because I'm subtracting the mx from each side, is equal to my b. So in order to find the y-intercept, I need to take my particular y value and subtract my slope times my x value. Now I'm going to go ahead and choose to use, I guess, this first point, the 6, 4. So if I use that point, you can see I've got an x value of 6 and a y value of 4. So I'm going to plug those points into this expression. So for y, I've got a 4 minus, now this is interesting, it's minus negative 2/3, right? Because my slope was a negative 2/3. So it's 4 minus 2/3, and then I'm going to multiply that times x, which is 6. And that is what b should equal. Well, let's simplify that a little bit. That's 4 plus 2/3 times the number 6. And if I multiply 2/3 times 6, right, that's 2 times 6 in the numerator over 3 in the denominator. So that looks like 12 over 3, which is equal to 4. So what I have here is I have 4 plus 4, and that's my y-intercept. So my y-intercept equals the number 8. Well, now that I have my slope is negative 2/3 and my y-intercept is 8, I can write the equation of this line. The equation of this line is y equals a negative 2/3 x and then plus 8. And it doesn't matter which of the points I plug in here, both of these points would definitely be satisfied by this equation. And both of these points would make this equation true because those points are on that line. And it's a good idea to check to make sure that you did really find the equation of the line. Okay, now go ahead and do the first one there on your own. This question is showing up because, well, it was a checkpoint quite a while ago, and it's good to make sure that we keep practicing, and we're always demonstrating that we understand and we're proficient. So solve the equations below. These equations have several rational terms in them, rational expressions, which just means that there's some fractions involved. One of the things that we use repeatedly is the method that we call, the textbook called fraction busters. So if I look at the second equation there, and I think that's the one that we're going to solve together, I can solve that by, well, I would begin by probably multiplying both sides by 10. Now, if you wanted to use a different value, you could use a 2 and then later do another step and multiply by 5. But I happen to know that if I introduce a factor of 10 in each of these parts, the fractions are going to completely go away. So let me go ahead and grab I don't know, a nice green color here. So I'm going to put parentheses around here. I'm going to multiply every single term on both sides by 10. So remember, terms are those things that are separated by plus minus. So the first term I see there is 1/2 times x. So I'm going to write this as, I'll write it as 10 over 2 times x. So if you look what I did, I multiplied the 1 times 10 in the numerator. And we'll simplify that in a minute. And then I've got minus 3 times 10. And that's going to equal a 10 over 5 times x. And then I'm going to add to that 2 times 10 over 5. So I wrote all that out because I want you to see that indeed in every single part here, I definitely introduced a new factor of 10, right? This didn't have a 10, now it does. This has a factor of 10, this has a factor of 10, and this has a factor of 10. So indeed, every single term on both sides picked up a new factor of 10. And I can do that, right, as long as I'm multiplying both sides of an equation by the exact same value, I get things that are equal. Because the left and right hand side were equal, if I multiply those equal things by the number 10, what I get is still equal. And it's really important that we not change the equation, but that we keep everything in balance and harmony. Whatever. So let's go ahead and just go to this. Now if I simplify, right, 10 over 2 is a 5x minus 30, and that equals 10 over 5 is a 2x, and then I have 2 times 10, which is 20 divided by 5, which is a plus 4. So it looks a lot nicer than the original equation. All those fractions are now gone. I'm going to go ahead and subtract 2x from both sides. On the one hand side, I'm going to have now 3x minus 30 is equal to a 4. And then I'm going to add 30 to both sides. And we now have that on the left-hand side, we're just left with 3x, and that is going to equal the number 34. And then finally, I'm going to divide both sides by 3. So that gives me that x is going to equal 34 thirds. Now that certainly is an interesting answer, but that doesn't mean it's incorrect. I'm pretty confident that we followed the correct steps. While we're here, I think it's really useful to think about how we would check that solution efficiently, especially in a classroom where you're allowed to use your TI-83s or 84 pluses. So let's take a look at that. If I plug this value in for the two x's, right, the x here on this side and the x on the right-hand side, if I plug in 34 thirds to those and do the arithmetic, I should get the same number on both sides of this equal symbol. And if I do indeed get the same number, then it should completely be equal on the same side. So I'm going to plug those in. So check out how I do this on my calculator. I just turn it on and I'm going to get 1/2. That's great. And I'm going to multiply that by 34 thirds. So 34 over 3, that's 34 thirds. And then I'm going to subtract the number 3 from that. Now when I do that, you can see I know that decimal, that's 2 2/3. But if you don't know it, you can just write it down. It's like 2.66, and the 6 repeats. The only reason why there's a 7 at the end is because it just rounded up. So now if I get the exact same thing on the right-hand side when I plug in this value of x, I know that I have the solution. So I'm going to do the same thing. I'm going to now do 1 divided by 5 times 34 divided by 3. That's the value of x. So 1/5 times 34 thirds, and then plus 2/5. Oops, I didn't get the divided by 2 divided by 5. So you can see I've got 1/5 times 34 thirds plus 2/5. And as soon as I press equals, you can see I indeed do get 2 2/3. So I know, because the left-hand side and the right-hand side are equal, that this is really the value of x that makes this particular equation true. So I hope that you do that. I really encourage you to check your answers like that, especially if they're kind of, they're not pretty answers and you want to check them with the fractions and you're intimidated by it. Please use your calculator and do that. So there's 4 copies of, or 4 different sets of triangles here that potentially could be congruent. If they're congruent, I would like for you to give me the triangle congruence condition that supports your conclusion. And let's just review those. There's 5 of them that we have. You can have 2 congruent sides and the angle in between those. We call that the side angle side congruence condition. You can also have 2 corresponding angle pairs and the side that connects them. We call that angle side angle. It's also possible that if you have all 3 pairs of corresponding sides congruent, the triangles are congruent. That's the side 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 congruence condition. Also, if you have 2 angles and then a non-included side, angle angle side, that's a valid angle congruence condition as well. And then the final one is if you have right triangles, you can establish that they're right triangles, and you have a pair of hypotenuses. The hypotenuses are congruent, and one of their legs pairs is congruent, then the triangles are congruent by hypotenuse leg. This looks like it only requires 2 pieces of information, but remember, it actually requires 3 because you must have a right triangle in order for that to work. So as I look at this, the first one, you can see that I definitely have a pair of congruent sides here, and I have another pair of congruent sides here. And then the one thing that I also have in addition to support it is this pair of, they're called vertical angles, right? Whenever two lines intersect, the angles that are right across from each other have to be congruent. So these triangles are congruent, and the condition that we have there, I hope that you can see which one it is, right? Take a look. It is clearly side angle side, right? I've got two pairs of sides that are congruent and the angle in between. So these are congruent by, side angle side. Sorry, that keeps moving around. And the other thing is, the problem doesn't actually ask for this, but it would be a good idea for you to write down which triangles are congruent. So if I was to say triangle B, and then to G, and then to I, BGI, that is congruent to triangle well, I hope you can see it. It has to follow all the corresponding parts. So the G has to be in the middle because that's there. But the other parts, it would have to be D and then G and then O. So it would have to hit G. I'm sorry, not G. First D, and then the G, and then the O. So that order matters because it's showing me the parts that line up. By the way, now that they line up like that, and I can see, for example, segment go, right? Segment go, that's the second and the last position. That corresponds with GI, right? And I can see that, yeah, GI, this segment, I'm sorry, GO, this segment, and GI are the two that were marked congruent. So that totally works. And also, you know, things that I didn't know were congruent, I can conclude are congruent now. So for example, if you notice that angle G right here and angle D right here, those are in the same spots, that means that this angle and this angle are congruent. Now that I've got those congruent triangles, I know that those angles have to be congruent. That's not the part of the problem. Again, I want you to just list the triangle congruence condition that supports it and list a triangle congruent statement like that. Let's see. You know, you look at it, remember sometimes the side that they both share is congruent reflexively. And if you think about that, I believe those are congruent because there's a side that they both have. But then you've got to know the right reason. For this one, let's see. Well, that's a challenge. Angle. The problem is side, side, and then angle is not a valid triangle congruence condition. But I'm trying to think here if there's something else that could happen. Yeah, I don't think these are necessarily congruent because like I said, we do have this side, right? And they definitely share this side. So I've got, you know, side and then this 30-degree angle. And then you can see here that I've got this side, and the 30-degree angle. But side and then angle does not lead to triangle congruence. What's deceptive, and if you think about this, I could definitely take this line, BT, and I could draw this line here. There's nothing that prevents it from being somewhere else because I don't know any information about that angle. So BT could be there, and it would still be the case that I'd still have the 320, and those angles below would be 30. So this is not something that leads to triangle congruence. And that's definitely what I have there. You can see there's side, side, and then angle, but it's not enough to conclude that those triangles are congruent. And then the last one here, I've seen this before, and I'm glad that we have both on this diagram. This diagram has that these opposite sides are, let me zoom out, I think it'll move around less. These opposite sides are both congruent, and the arrows mean parallel, right? The arrows The arrows do not mean congruence. They mean that they are parallel to each other. So I have a pair of opposite sides, IT and OM, that are both parallel and congruent. And I want to point out a couple pairs of angles you may not think about. But whenever I have a pair of parallel lines cut, those don't look parallel, and if I'm trying to prove a point, I should try and make it look a little bit more convincing. But if I have a pair of parallel lines, and I cut those parallel lines with a transversal, I get some angles that are called alternate interior angles, and they have to be congruent. So for example, this angle right here is congruent to this angle. They're the same size. Now, if you look at it in this diagram, this angle down here at M and this angle up here at I fit that condition. There are definitely two angles formed by parallel lines, and then this transversal IM cuts through them. So because of that, these have to be congruent angles. And I could actually go the other direction too, right, with OT. If I was to draw an OT here, you can see that I've got this little angle up here and this angle down here. They have to be congruent because, again, there's parallel lines cut by a transversal. So that forces this angle to be congruent to this angle. So I really pointed this out, kind of gave it away, but be aware of that. When you see parallel lines, be thinking to yourself, are there any angles that come out of that that perhaps could be used to establish congruent triangles? So, and I think you could figure out what triangle congruent statement applies there and which triangles are congruent. So solve the equations below, include a check for each of your solutions. As you solve this, really be careful with the second one when you're using the distributive property. Make sure that when you are moving that 2 into the parentheses, that both the 3x and the 7, positive 7, are getting a factor of 2. For that first one, if you take a look at it, I think the method that I would recommend is, well, first of all, let's get the radical part alone by, I guess, adding 4 to both sides. So if you add 4 to both sides of that, that becomes the square root of 3x is equal to 9. And now if you think about the look inside method, this equation generally says, look, I've got the square root of something equaling the number 9. So just pause for a minute. What number, when you take the square root of it, produces a value of 9? Right? What is that? So if I'm looking inside, I know that that thing inside has to equal whatever it is that would give me a value of 9 when I took the square root of it. So the square root of something gives me 9. What is that thing? And then you can take the 3x, right, the thing that's inside, and set it equal to what that value is, and then solve for x. By the way, once you get that value of x, please take it and plug it back in here and make sure it works. Same thing for the second one. Once you get the value of x, make sure you just grab your calculator and just go, 2 times, open parentheses, 3 times your x that you found, plus 7, close parentheses, plus 1. Write that number down, and then check that that value is the same on both sides. So that's the second one. Give the equation of the line that goes through point C and is perpendicular to the line that goes through line AB. Show all of your work. So the general idea here is I've got this line AB, and I want to come up with the equation of a line that comes out of C like this and forms a right angle. So this is the line that we're looking for. What is it exactly? What's its y-intercept? What's its slope, etc.? Well, to do that, I'm going to, first of all, identify the slope of the line that I have. And if you look at it, this line has a slope of down 2 over 1. Right? I just went down 2 units and then to the right 1 unit. So the slope here is negative 2 over 1, which is negative 2. So this line has a slope of negative 2. Well, when I rotate a line on the Cartesian coordinate plane, if I flip the rise and the run values, when I rotate it through 90 degrees, it's always equivalent to flipping the rise and the runs. and we demonstrated that earlier in the year. So it's just a fact that that 90-degree rotation occurs whenever you flip the rise and the runs. And if your slope was negative, as it is in this case, when you rotate through 90 degrees, it has to become positive. So the slope of the line that we're looking through, right, this line that goes through C, would have to be positive 1/2. So this is our target line slope, right? It has to equal 1/2. And in fact, if I look at this now, I can go up 1 and then over 2, and then up 1 and then over up 1 over 2, and I kind of get a much better idea of what exactly that line is going to look like. I don't quite know, and I wish I made that graph paper a little bit bigger, but it's definitely the line that goes through here. Now, what I need to know, though, is I need to know the y-intercept. Now, you might think, well, we're out of luck, except we do know the point C, right? We know that C is at the point x is 3 and y is -2. So if you think about that, right, I've now got a particular x and a y for that point. And if I plug those into this equation, y equals mx plus b, where I use the slope m that I have, I use the y value down below, right, that's -2, and I use the x value 3. If I plug all those things in, I can definitely solve for b. And at that point, I would know both the slope and the y-intercept, so I could rewrite this again. Y equals something times x plus something, and write the actual equation of the line. And again, I did this problem just like this kind of earlier in this, so you can review your notes from that. So the last series of questions I'd like for you to do involve 3 systems of equations. The first one's 24x minus 4y equals 12, and the other equation is y plus 3 equals 6x. And I'm asking you to solve these using any of the methods that we have, either equal values method, substitution, or elimination. I'd like for you to show all of your work in the box provided, and then also make sure that you include the method that you use. So for example, if you choose to use, I would probably use substitution. Write down that you're using substitution. Why can't I spell substitution? And then show your work in this box. I realize these boxes seem a little small on my screen. I don't know if they're small on your paper. But then once you have the work shown, record your answer over here as an XY ordered pair. By the way, I said I would use substitution for this one. What I would probably do is subtract 3 from both sides, and I would get that y is equal to 6 times x minus 3. That, it turns out, is a great value for y to put into the first equation. So you'd have to distribute that -4, and I anticipate that probably a spot where you would likely make a mistake is you'd have the 24x minus 4 times the quantity of 6x minus 3. That does equal 12. But notice that I need to multiply both the 6x and the -3 by -4. So that would become 24x minus 24x, and then plus 12, and then that equals 12. Well, that's interesting, isn't it? So that leads me to this statement, right? Because these cancel out, I'm left with 12 is equal to 12. Now, I want you to think about this and read this sentence above. Remember, a system of linear equations may have one solution, may have 0 solution, or it may have many solutions. So you might want to think about what those lines look like, and if you rearrange them, what's going on here, because it looks like it doesn't have one solution, and I won't say any more than that. Again, actually, you know what? That's kind of interesting. On this equation, didn't even think about it, but look at this. The second equation tells me that this is 4x. If I wanted to, I could just replace that whole 4x with that expression. Never thought about that before, but that might be a nice way to use substitution. And you can use it again. You don't have to use each method once. You can keep reusing them. And then on this last one, probably I would use substitution also. Um, so I don't know if you want to rearrange it and try and use equals values, you can, but that looks like it's really set up for substituting. All right, so I look forward to seeing your XY solutions written here. Remember, on Monday, we are taking the Chapter 7 individual test down in the dungeon. There is a homework assignment on the list, but it is not due until Tuesday. So the next one on the list is due Tuesday. It's not due today, and it's not due on Monday, the day of the test, but Tuesday. Have a great weekend. I look forward to seeing you on Monday.